There are places in our solar system so distant, so cold, and so alien that even light takes hours to reach them. Yet in these silent, icy frontiers, something extraordinary may be waiting. In 1977, two machines, Voyager 1 and Voyager 2, left Earth. Tiny, golden-armed emissaries carrying our hopes, our knowledge, and a map to find us. Their destination? The outer planets? Their mission? To unveil the deep architecture of our solar system. What they found was not emptiness, but breathtaking complexity, moons with hidden oceans, rings older than memory, and a stolen world, Triton, circling Neptune backward, whispering secrets of capture, chaos, and perhaps creation. Farther still, beyond the reach of Neptune, icy dwarfs wander through the Kuiper Belt, ancient relics from the time before planets, Pluto, Charon, Eris. Once thought barren, now they challenge everything we thought we knew about life, chemistry, and evolution. Could life emerge without sunlight, in oceans beneath ice? Could evolution choose silicon instead of carbon? Could beings exist in lakes of liquid nitrogen? On Earth, intelligence arose in warmth, in water, under a forgiving sun. But what if intelligence, true conscious awareness, can rise in the dark? What if the mind is not exclusive to Earth, but a cosmic inevitability? This is the story of frozen giants, lost moons, and alien possibilities. A journey to the edge of our solar system, and perhaps to the edge of life itself. Triton, Pluto, and the outer solar mysteries. Life in the cold.
The outer gas giants align every 175 years to produce the most direct and energetically efficient path from Earth to every planet. The planning of an extensive tour of the outer planets and their moons, known as the Voyager mission, began in the middle of the 1960s, when a rare chance for exploration between 1976 and 1978 was found. Budget restrictions at the time the Voyager spacecraft was launched in the summer of 1977 forced a cut of the Grand Tour to an exploration limited to the Jovian and Saturnian systems. Still, they started Voyager 2 on a path that allowed them to travel to Uranus and Neptune. Funding was set aside to reroute Voyager 2 towards the outer gas giants, so restoring the original Grand Tour schedule following the wonderful success of Voyager 1 and 2 in revealing the wonders of Jupiter and her 4 unique moons, as well as Saturn with her magnificent rings and enigmatic moon. Following its closest approach to Saturn on August 25, 1981, the spacecraft's course was changed to point toward Uranus and Neptune. 8 years later, Voyager 2 reached the closest proximity to Neptune and its most important moon, Triton. Most of what we know about those two entities comes from that meeting. Although no spacecraft has ever visited Pluto and its co-rotating companion, Charon, terrestrial observations have produced plenty of information to prepare for their first meeting with the robotic probe, New Horizons, to arrive in 2015. According to the data, Triton and the Pluto-Charon system are interlopers, coming from somewhere outside Neptune's orbit. Pluto and Charon were first classified as a planetary pair because of their orbit around the Sun. But in 2006, they were changed to dwarf planets after the discovery of more sizable asteroids orbiting the Sun. Technically considered a moon, Neptune's adoptive parent most likely took Triton from a similar population of dwarf planets. The creation of the solar system was not perfect. At this point, 4.5 billion years into existence, the solar system has evolved into a sun and 8 planets, yet traces of its primordial formative stages still appear unappreciated. The first accretion phases consisted of the progressive aggregation of gas and dust into particles, boulders, and sufficiently big objects today known as asteroids. Attracting smaller asteroids into their gravitational fields, the biggest asteroids grew in mass until they finally generated planetesimals. 4 planetesimals would produce the 4 terrestrial planets: Mercury, Venus, Earth, and Mars, within the inner solar system. 4 large rocky planetesimals in the outer solar system gathered enough gases from the Sun's formation to develop into the 4 gas giant planets: Jupiter, Saturn, Uranus, and Neptune. As they grew, the 8 survivors collected most of the smaller asteroids in their orbits. As such, the relatively close rocky planets cleared most of the inner solar system's asteroids. Though far apart, the gas giants had enough mass to clear the protostellar disk from inside Jupiter to somewhat beyond Neptune. As they orbit in the same direction as their parent planets and are roughly in the ecliptic, the flat plane covering the orbits of all 8 planets, several asteroids and planetesimals that evolved into moons, most certainly formed concurrently with their parent planets. Mars's and Jupiter's distance is too great for either planet to clear the asteroids in the intervening space. Hence, a belt of unprocessed asteroids remains in that area, possibly representing an incompletely formed planet. Another theory holds that asteroid debris in that area may have come from catastrophic collisions between fully developed planets. A vast swath of asteroids stretches 6 billion kilometers beyond Neptune's orbit to the periphery of the solar system, without a sufficiently large planet to incorporate them. Named for Gerard Kuiper, who first suggested their existence in 1951. The Kuiper Belt is the outer band of asteroids. Although the Irish astronomer Kenneth Edgeworth had put out a similar idea 8 years earlier. Asteroids ranging in size to several hundred kilometers have enough gravitational force to take on a spherical form. When bodies close to 1,000 kilometers wide come together, they generate enough heat to melt their insides, leading to the formation of a core and mantle. The mantle of asteroids contains different amounts of water ice in the outer solar system, where cold temperatures let water adhere to mineral substrates. As a result, the big asteroids in the Kuiper Belt and the significant moons of the gas giants mainly consist of icy bodies with densities between 1.5 and 3.0. Pure water has a density of 1.0. Dwarf planets are a type of celestial body that revolves around the Sun. Certain. Planets have moons, which are celestial bodies that orbit other planets. Formation theory holds they are essentially the same. Like stars, asteroids often pair off. Pluto and Charon serve as examples. We will discuss Triton's potential membership in such a binary system below. All 3 are snowball worlds, typical of those widely found in the Kuiper Belt. Triton's orbit Neptune qualifies it as a moon. Pluto and Charon are labelled as dwarf planets since they orbit the Sun. All 3, however, have their common source in the Kuiper Belt, an asteroid and planetesimal region around the Sun outside of Neptune's path. This outline presents a reasonable narrative of their beginnings and positions. One is our solar system's protostellar cloud of gas and dust, which had enough heavy elements to be considered mineral-rich. Consequently, dust particles, rocks, and many boulder-sized accretions formed as the cloud collapsed toward its gravitational center. 2 is the more than 99.9% of the protostellar cloud's mass fell into the Sun, while the rest scattered into the disk. 8 planetesimals exceeded their counterparts in size, drawing all smaller objects within their orbital trajectories into their gravitational fields, either by chance events or principles not yet understood. Emerging from the Sun, the 8 full-sized planets revealed the 4 outer planets sufficiently far apart to preserve significant amounts of hydrogen, helium, and other gases. 3 million smaller accretions from the protostellar disk did not combine into fully developed planets in their residual state. Some objects, like Triton and the Jovian moons, became satellites circling planets. Some turned into asteroids, circling the Sun either inside the vast Kuiper Belt or between Mars and Jupiter, some 6 billion kilometers outside the orbit of Neptune. 2. Some asteroids reached the necessary mass to produce enough heat through radioactive decay. This, combined with the kinetic energy from constantly colliding with smaller bodies, caused the melting and separation of the interiors of these asteroids, previously classified as dwarf planets. Spherical planetesimals boast metallic cores, mantles of minerals and water, and diameters of nearly 1,000 kilometers or more. Scientists designed multiple binaries, also known as planetary pairs, to orbit a mutual center of gravity. 5 here. With an unknown diameter between 2,400 and 3,000 kilometers. Eris is the biggest known dwarf planet in the Kuiper Belt. Triton, 2,700 kilometers, and Pluto, 2,300 kilometers, most certainly started in the Kuiper Belt, given their size. Their surface temperatures were low enough to condense nitrogen and methane at that distance. The proximity of the great planet Neptune periodically disturbs objects in the Kuiper Belt. The Sun drives some objects into more eccentric and oblique orbits. Pluto and its smaller satellite, Charon, underwent this phenomenon, whereby they orbit the Sun in an elliptical path that places them closer to the Sun than Neptune, for 20 out of their 248 years, in gravitationally locked synchrony. More massive planets have accumulated Kuiper Belt objects. This seems to be Triton's fate, maybe the last echo of a binary dwarf planet system. Triton entered a retrograde, oblique, and eccentric orbit around Neptune, driven by the nature and intensity of the contact. In 8, Triton's interactions with Neptune most certainly produced enough energy to melt water in its mantle. Simultaneously, the eccentricity of its original orbit sustained tidal heating, capable of preserving liquid water for almost 1 billion years, even if the surface would have most certainly frozen quickly. 9th. Triton's retrograde orbit, combined with friction from debris resulting from its collision with Neptune, has produced viscoelastic tidal forces that have regularized its orbit and almost made it circular. Still, radioactive decay in its core could keep releasing internal energy. 10th point. Pluto, Charon, and Triton's similar bulk compositions help to provide circumstantial evidence supporting a familial resemblance. Having a density 0, they consist of other frozen gases, 1/3 water ice, and roughly 2/3 rocky minerals. Because of their great tilt relative to the ecliptic plane, both have tenuous atmospheres mainly composed of nitrogen that dissipates from their polar regions, orienting both toward and away from the Sun. 11 gravitational drag produced by Triton's retrograde orbit around Neptune draws Neptune closer. Triton will eventually get close enough to Neptune to shatter apart or collide with its adopted progenitor. Pluto and its smaller companion, Charon, are a team, probably formed at the same time using the same process. Every 6.38 Earth days, they spin around one another on their respective axes. Thus, they maintain the same attitude toward one another. No spacecraft from Earth has visited Pluto or Charon. Hence, terrestrial observations have been the only means of knowledge about their features. Terrestrial observations cannot provide surface detail on Pluto. Charon is not yet large enough to determine even that degree of detail. For simplicity's sake, we will just discuss Pluto. We will recognize that our remarks about Pluto might not always apply to Charon. Pluto most certainly started in the Kuiper Belt, since it spends its orbital cycle mainly in that area. Its orbit is quite elliptical and inclined over 17 degrees relative to the plane of the orbits of the other planets around the Sun. These properties point to short-period comets, also thought to come from the Kuiper Belt. Pluto's axial tilt of 122 degrees and 3:2 orbital resonance with Neptune produce its retrograde rotation relative to Neptune and most other planets. Pluto's 2.03 grams per cubic centimeter density suggests that the dwarf planet comprises about 70% rock and 30% water ice, along with darker areas suggesting significant topographical variation. The surface shows highly reflective bright areas, suggestive of frost or ice. Following Sun's moon, Iapetus, Pluto shows the second-best degree of surface contrast in the solar system. Without higher-resolution surface images, evaluating geological activity on Pluto is impossible. According to spectroscopic data, Pluto has a fragile atmosphere, mainly composed of nitrogen, and minute amounts of carbon monoxide and methane. The surface temperature runs about -230 degrees Celsius. As a result, the surface consists mostly of nitrogen ice, with little trace of frozen carbon, monoxide, methane, or water ice. The seventh largest satellite of the solar system, Triton, is Neptune's moon. It moves against the direction of Neptune's rotation, almost circularly around Neptune in a retrograde manner. Triton's orbital plane is much inclined relative to the ecliptic. As Neptune revolves around the Sun, Triton's poles alternately face the Sun, producing notable seasonal fluctuations in the polar regions. These orbital features point to an origin different from Neptune's accretion. Characteristically of large Kuiper Belt objects, Triton has a density of 2.08 grams per cubic centimeter and a diameter of roughly 2,700 kilometers, surpassing Pluto's. Most astronomers agree that Neptune obtained Triton from the Kuiper Belt. According to a reasonable model, Triton might have started as part of a dwarf planet pair and then interacted aggressively with Neptune to split off its friend. Triton's dimensions and density suggest a composition ranging from 2/3 to 3/4 rocky material, with the remaining fraction made of water, ice, and other frozen gases. On its surface, delicate yellow to peach-colored tones suggest the presence of organic compounds, maybe reaction products from methane. 2. The blue-green areas close to the equator might point to the existence of nitrogen and nitrile-based frost or ice. At -235 degrees Celsius, Triton's surface is the coldest in the solar system. Molecular nitrogen N2, hydrocarbons and nitriles condense at this temperature. Along with small amounts of methane, carbon monoxide and possibly ammonia, the surface is thought to consist of frozen nitrogen, water, and carbon dioxide listed in sequence of frequency. Triton has a fragile atmosphere mainly composed of methane and nitrogen. A tenuous haze covers 5 to 10 kilometers above the surface, and dark material expelled from geysers shows signs of airflow. High-energy particles, coming from Neptune's magnetosphere, generate organic compounds from methane and nitrogen in the top atmosphere. 3. Although some must climb to the surface, experts argue their lifespans are limited. With some features found on other celestial bodies and others unique, Triton shows a rather smooth but varied topography. Triton's large axial tilt causes its poles to orient nearly exactly toward the Sun in summer and away from it in winter. Triton's south pole was pointed toward the Sun during its interaction with Voyager. Thus, The clear difference between the polar and equatorial regions could have resulted from that seasonal alignment. The southern polar region, comprising a mottled white overlay, shows a substrate ranging from pink to peach. Grey streaks constantly point east. These are considered waste products from geysers, most likely erupted when continuous sunlight heats the colored material under the translucent layer of frozen nitrogen on the surface. Emitted from fumarole-like apertures, nitrogen and particulate matter reach altitudes of 8 kilometers, and then are carried downwind for distances up to 150 kilometers. At the northeastern boundary of the South Polar region, 3 notable patches are visible near the eastern horizon. Examining this area closely reveals that these are regularly dark formations, possibly basins, bordered by white material, most likely nitrogen frost. Comparatively to New Jersey's size, the lower proper measurement's largest area is almost 200 by 100 kilometers. They are unique even though they resemble lag deposits from arid lakes on Earth. Their presence in the change from polar to equatorial zones is of yet unknown importance. Found in the western equatorial region, the cantaloupe terrain is a unique topographical feature absent elsewhere in the solar system. The gourd gets its name from how much it resembles cantaloupe skin. The 30 to 40 kilometer diameter depressions have walls several hundred meters high. Their dimensions and spacing are too homogeneous to fit any classification of impact craters or volcanic calderas. Diapyrism, the theory most likely explaining their formation, is the upward movement of less dense material across a thicker crust. Though Triton's terrain is unique, it shows grooves of troughs and ridges that closely match those seen on Europa and other icy satellites. The cantaloupe terrain combines traits unique to Triton with processes identified elsewhere. Much of Triton resembles large volcanic plains like the Mare of the Moon. These areas seem quite complex at a high resolution, showing a sequence of fumaroles or calderas, clearly defined ridgelines and depressions, maybe resulting from faulting and sapping. Extensive flat depressions similar to those formed by major flooding could have come from lava spreading during cryovolcanic eruptions. The observation that the surface seems rather young, as shown by the fact that the crater counts are 4 to 5 times lower than those on the much more minor planet Uranus, supports this point of view. Triton's surface's estimated young age, between 5 and 50 million years, is a major factor supporting the presumption that it is either currently or has recently shown geological activity. The overlay of modern surface features on ancient ones implies that resurfacing on Triton has taken place for a long time. Moreover, new data on geyser eruptions in the southern summer show seasonal dynamic activity. The large resurfacing is mysterious, since Triton's almost circular orbit casts questions about the possibility of tidal fluctuations, with Neptune providing Triton with energy. Energy for these eruptions comes from interactions with other Kuiper Belt objects, or from ongoing radiogenic decay. We don't know much about Pluto. Readers know that we do not hesitate to participate in informed speculation, yet we cannot offer reasonable ideas in cases of limited information. Triton and Pluto are almost identical in their rotational axis measurements, origin and tilt. We will thus look at the conditions suitable for life on Triton, realizing that all signs could point to the possible existence of life on Pluto. Shortly after New Horizons arrived at Pluto in 2015, we will have the information required to create reasonable hypotheses about that celestial body. We will thus limit our attention to our knowledge of Triton. 30 astronomical units from the Sun. Triton absorbs 1/900th of the solar intensity reaching Earth. Even if systems had evolved to maximize limited light for biological purposes, it seems unlikely that any liquid could survive, except momentarily, sufficiently near the surface of such a frigid planet to enable biological use. Thus, we have to investigate energy sources other than light to identify possible life on Triton. There is organic chemistry potential. Clearly visible close to the surface are methane and inevitable reaction products. The conversion of methane and nitrogen into alternative organic compounds apparently occurs in the upper atmosphere, though to a smaller degree than on Titan. Whether enough organics exist on Triton in combination with other chemical reactants required for energy-yielding reactions, such as oxidation-reduction cycles, is unknown. Triton shows a certain degree of chemical complexity based on its intriguing coloration. The brown material released and carried downwind from geysers resembles tholins seen on Titan. That might be contaminated water. Regarding chemical energy sources for possible life on Triton, the conclusion is probably that they do exist. Many signals suggest that geothermal energy is still active on Triton. The young surface, the flat areas that look like they were shaped by large ice volcanoes, the many pits, and the absence of large craters that show regular eruptions all indicate that heat from inside the Earth is causing geological activity. One can obtain heat with bioenergetic potential from within. Neptune's magnetosphere is fragile and magnetic energy is useless. Thus, this is probably impossible. Still, if large liquid reservoirs under the surface, like oceans, exist, other kinds of energy could be present, such as kinetic energy or osmotic and ionic gradients. This is a real likelihood. Carbon is the main building block of life. It is present on almost all celestial bodies except stars under many different conditions. Thus, it has to be considered the main candidate for the concerned biomolecule. Triton clearly includes organic carbon. Still, Triton would be the main competitor if any place in our solar system could make silicon a basic component for life. Silane. Compounds have a structural resemblance to hydrocarbons. Silicon replaces carbon. Polysilanes are likely to form under very cold temperatures, without liquid water, without reactive oxygen, with little carbon available, using solvents like methane or methanol that work well with silanes, and under high pressure. Triton meets most of these criteria. Although the subsurface stretches to an unknown depth and is too cold for pure water to exist in a liquid form, it is most likely under enormous pressure and contains different elements, such as ammonia, which would raise its melting point. Furthermore, low enough temperatures allow methane and methanol to liquefy. Other organic forms of carbon are rare, while frozen reserves of carbon monoxide and carbon dioxide are the only sources of oxygen. Triton has conditions fit for silanes, a cold environment, effects from celestial bodies on cold planetary surfaces, and UV light emitted from ice-encased silicate particles. One clear downside of the possible frequency of silanes is that if there is enough methane to act as a solvent, it could supply enough carbon to rival silicon. As such, it seems unlikely that silanes would be fundamental constituents of Triton's possible life. However, we don't know enough about how silanes act in various chemical mixtures under high pressure and very low temperatures to completely rule them out as potential building blocks for life on distant celestial bodies in our solar system. Silanes are rare in meteorites and other interstellar sites, but the protostellar disk W33A is an exception. Hence, different conditions could let silanes turn into biomolecules. We cannot rule out the possibility of Triton existing in such a world. 11.5.3 Tritonic solvents for life. 2. Questions define the possible presence of solvents supporting life on Triton. First, their chemical composition is important. Second, whether they exist in a liquid form in any hypothetical habitat on Triton is also important. At least 25% of Triton's bulk composition is water, but it has to live much below the surface to stay liquid. There is strong evidence for cryovolcanism, suggesting that occasionally a mixture of subterranean liquids mostly water, reaches appropriate temperatures to erupt to the surface. Still, the percentage of the lava from cryovolcanism made of water against that made of methane, nitrogen, or ammonia is unknown. Like Triton, underground reservoirs of liquid water ammonia may exist, but they require much higher temperatures, -80 degrees Celsius, than those near Triton's surface. Liquid methane is a better choice, but the critical question is whether methane can be sufficiently concentrated to generate notable solvent reservoirs. Nitrogen, 1.2, shows outstanding promise. At almost -235 degrees Celsius, frozen nitrogen covers Triton's surface. At -210 degrees Celsius, N2 crystallizes. At -196 degrees Celsius, it moves to a gaseous condition. As such, it stays liquid within a small thermal range, most likely existing at a depth below Triton's surface. The transparent layer of frozen N2 on the surface might be thin enough to enable a greenhouse effect to warm underlying colored compounds. It is conceivable that there could also be enough to create small reservoirs of liquid N2 if enough energy could be extracted from the summer sun to produce geysers. Liquid N2 could be present within the layers of frozen N2, or a fluid film between the frozen N2 above and the frozen H2O below. In liquid form, nitrogen has a low dielectric constant and a zero dipole moment. Hence, it is a non-polar solvent unfit for carbon-based biochemistry. That could be the solvent polysilanase can reach to achieve dynamic interaction and a degree of complexity. Triton has an extremely low surface temperature and inadequate atmospheric pressure for any liquid to remain stable. Under the surface, 2 microhabitats and 1 main habitat are possible. The first microhabitat consists of tiny water ammonia saline ice inclusions buried in the mantle's main water ice. These inclusions cannot develop when the temperature is close to the surface. At greater depths, though, heat from inside, higher pressure, and a lower freezing point of dissolved ammonia and other substances can create stable liquid inclusions that support salt-tolerant, water-based, carbon-based life forms. The second microhabitat comprises thin layers of liquid N2 atop frozen N2, with a solid layer underneath, either frozen H2O or liquid N2 incorporated within frozen N2. The seasonally triggered geysers show the liquefaction of frozen N2 and seem to result from the solar heating of subsurface volatile. Thin layers of liquid nitrogen, sometimes known as liquid nitrogen inclusions, could thus exist. The third habitat for life under Triton's surface would be this one. After its acquisition, Neptune most likely captured Triton, which then became surrounded by remnants of a global ocean. The cantaloupe terrain and presumably continuous cryovolcanism point to subterranean liquid water existing on Triton. The dynamic activity of subsurface liquid reservoirs most clarifies the cantaloupe terrain. Unmatched cantaloupe terrain in the solar system suggests that any resulting formations may have an odd mix of subsurface liquids. Still, given the expected water content in Triton's bulk composition, it is most likely a water-based mixture. Minimal heat in the core produced by Triton's circular orbit leads to the theory that radioactive decay in the core preserves sufficiently high temperatures to melt water and cause a cryovolcanic eruption. Triton offers our first example of a world in which life most certainly did not arise early in planetary history. Our limited knowledge of the early eons of a body's existence in the Kuiper Belt supports this view. But consider the challenges facing the beginning of life on a dwarf planet far from the Sun, over 30 astronomical units. While some organic molecules and water would be available, energy derived from sunlight and magnetic fields would be negligible. Like larger planets, catastrophic collisions were probably familiar, but on dwarf planets, cooling happened more quickly following the termination of their equivalent of the Great Bombardment. especially for smaller ones like Triton and Pluto. While we understand the possibility for quick life creation, a more cautious perspective holds that life on Triton most likely started following Neptune's capture instead of before. This is the scenario we propose for the possible evolution of life on Triton. At first, the global ocean, made liquid by the capture event with Neptune 6, would have been the only candidate among our 3 suggested habitats for life on Triton. According to current models, the great mass of water and thermal energy would have kept it liquid for hundreds of millions of years, even with fast surface freezing. Surface access would have been useless, since sunlight for phototrophy would have been rare. Perhaps some O2 for redox reactions was produced by the UV photodissociation of H2O. Still, chemoautotrophy looks more likely near or on the ocean floor. Triton was an early Europa as it set its initially unusual orbit around Neptune. The evolutionary paths for life on both worlds might have been quite similar. This documentary shows how life on Triton could have evolved based on scientific theories. Based on water and carbon, life most certainly started with heterotrophic proto-cells living at the bottom and eating organic compounds from their surroundings. From these ancestral chemoheterotrophs, step 1, microorganisms most certainly evolved. They could be methanogens or sulfur-ion bacteria-like microorganisms, but we don't know. We will refer to them in general terms only. Very soon after, a lithoautotroph most certainly evolved, step 2. The early descendants of the last common ancestor, life on Triton, may have also included a series of thermotrophs, ionotrophs, or kinetotrophs. Perhaps also present were detritive, step 10. Presumably hundreds of millions of years were enough for complexity to develop, allowing macroorganisms to filter feed while stationary on the ocean floor. Step 11. Drift like jellyfish. Step 12. And finally adhere to the ice ceiling at the apex of the water column. With so many food producers, consumers would have surely evolved. Step 14. Moreover, the ice ceiling would have created a new habitat by means of liquid inclusions inside the ice. Pre-adapted lono or osmotrophs should have profited from the higher salinity of these aquatic microhabitats, step 15. Equally reasonable is step 16, sequestration of psychrophilic chemoautotrophs. The evolution of these ice-dwelling species would not have markedly deviated from their open ocean ancestors. Triton's orbit gradually turned more circular. Tidal heating would have dropped, but enough heat would have stayed in combination with radiogenic heating from the core to keep an uncertain ocean volume in a liquid form. The temperature outside would drop to extremes never seen in Europa, or eventually any other planet in the solar system. The closest analogue was frigid Titan. At this point in Triton's history, it would have lessened resemblance to Europa and more resembled Titan. Because of its unique mix of organic compounds and their degradation products, hydrophobicity would have begun to reflect a commendable way of living. How can we get from hydrophilic organisms to such different entities? Should we suggest the possibility of life on Triton, we must fully embrace that survival at low temperatures. As low as 40 degrees above absolute zero depends on life in liquid nitrogen. In an oxygen-deficient hydrophobic environment, such as liquid nitrogen, silane might be a better biomolecule backbone. According to the theory, nitrogen-based silane-derived life forms might have settled into the minute cracks, fissures, and inclusions that would eventually form in frozen nitrogen. Appropriately, Triton provides a structure for thinking about this problem. Like Triton, where the challenge lay in changing life from water-based to ethane-based organisms, such an evolution could have happened on Triton using two processes. First, new life might have started in the fissures or inclusions within the liquid nitrogen. producing a chemoheterotroph fit for nitrogen-deficient conditions. Instead, transitional forms changed from using hydrocarbon materials to silane-based structures through interactions between H2O ice and NZ ice, step 17. Originally a mix of H2O and ammonia H3, transitional forms helped to ease the change from H2O to N2 as a solvent by mixing NH3 and N2. The viability of resolving the problems resulting from the different melting points of H2O, NH3 and N2 is still uncertain, as is the possibility for biochemistry in these solvents. Though it seems unlikely, we argue that it is worth thinking about. If some N2-tolerant chemotrophs settled in liquid nitrogen, fully independent forms could have developed to live in either small pockets, step 18, cracks, step 19, or both. Biofilm mat-like organisms proliferating on frozen surfaces may have caused a consumer to arise in liquid nitrogen, step 20. The evidence suggests that liquid nitrogen contains a minimum of 2 trophic levels of silane-based life, most likely forming the most unusual ecosystem in this area of the Oort cloud. Our solar system initially absorbed minor planets, Tritons and Pluto into major planets. Pluto stays in the Kuiper Belt of asteroids past Neptune, in the region of its origin. Its orbit approaches the Sun closer than Neptune's about every 260 years, then withdraws with its binary companion, Charon, to a distance of 40 astronomical units from the Sun. Initially taken from the Kuiper Belt to serve as Neptune's largest satellite, Triton is now a permanent resident. From a great distance from the Sun, both bodies show characteristics common to asteroids. 2/3 to 3/4 of their mass is rock. The rest is water. The ice solidifies as firmly as stone, making it among the coldest objects ever known, at least externally. Along with methane and its reaction products, including nitriles, it also consists of nitrogen, a major volatile element. Enough nitrogen envelops the surface to create a tenuous atmosphere of N2, along with minute amounts of usual gases, including methane, carbon monoxide, and carbon dioxide. Among the most odd celestial bodies in the solar system is Triton. Its extreme cold-colored chemicals, notable tilt-producing seasonal variations between the equator and the poles, and, likely, presence of subterranean liquid reservoirs define its surface as familiar and unique. It's quite rocky and mountainous, exotic by all terrestrial criteria. The life chances there seem difficult but not impossible from our vantage point. According to Triton's formation and capture history, a global ocean surrounded the dwarf planet turned satellite after Neptune acquired its orbit. Organic compounds and several energy sources abound. Thus, enough time should have passed for life to evolve. Despite being covered by a frozen crust, a trajectory similar to that of Europa is possible. Triton stands out in that it evolved from a Europa-like satellite to one more like Titan, where organic chemistry is more clearly evident. Still, Triton cooled to the degree that nitrogen crystallized, surpassing Titan. 3 possible microhabitats from this event are aqueous inclusions within water ice, large subsurface pools or an ocean, and liquid nitrogen reservoirs. If life started in water on Triton, it most certainly followed a major evolutionary path similar to that on Europa. Creating a liquid nitrogen environment allowed for a unique opportunity. Organisms that can tolerate nitrogen, possibly relying on silane building blocks in whole or in part, began to inhabit the cracks or spaces within the liquid nitrogen. Moving from a Europa-like here to there could have presented difficulties. But nature shows creativity beyond human capacity. Our study of the possibilities for life in our solar system strongly indicates that Earth is the only planet with intelligent species. the only one where at least one species has evolved technology, and most likely the only celestial body orbiting our sun supporting organisms of considerable size, complexity, and diversity. We shall now investigate the causes of the development of life with those traits on Earth, and the consequences for the possible existence of sophisticated, intelligent, technologically developed life in other worlds. Significant microbial biomass and the emergence of big and sophisticated organisms are outcomes of the evolution of life on Earth. It has achieved this by enabling the single cell, the microscopic unit of life, to proliferate into coordinated colonies, producing significant living entities. Furthermore, cellular differentiation and specialization development have generated quite sophisticated organisms. Their inherent complexity has driven them to diversify into many forms. As a result, the biosphere of the Earth shows great variety, including simple and sophisticated organisms, as well as big and small ones. Whether such entities of such size and complexity exist elsewhere in the solar system is unknown. There is no proof of their existence, but we cannot discount the likelihood until we look at Europa's icy crust or Mars's lava tube caverns. Their world is another one. Why support our claim? Why should one give multicellular macroscopic life forms on nearby celestial bodies some thought? Analyzing some elements that have enabled the development of significant size, complexity, and diversity on Earth will help one understand where and under what conditions such events might occur on other planets. Organisms get rather large when their biomass sustaining them is proportionately higher. The amount of accessible energy determines biomass, essentially. Our analysis of biomass pyramids from Film 3 reveals that many top consumers rely on having enough primary consumers and producers to supply the nutrients and energy required to expand the organisms at the top of the pyramid. Similar dependability on a plentiful energy source characterizes complex food webs and sophisticated ecosystems. This money will help a great range of producers who can provide large numbers of different groups of consumers. One of the most effective ways to energize living systems is to use the almost infinite solar energy source of the Earth to promote the planet's biodiversity. Many big living entities found in ecosystems on Earth rely on chemoautotrophs, which get their energy straight from chemicals in the surroundings. These models act as analogues for what we postulate as the main energy source on planets possibly hosting life in dark, subterranean environments. Deep ocean vents are the only sites on Earth where species can reach notable numbers. The ecosystems they support are not widely scattered. Microbial in scale are all other life forms, depending on chemoautotrophy at the producer level. Although no terrestrial precedent exists except deep ocean vents, a significant scale obtained from any other energy source investigated in this book is possible. The atmosphere and biosphere interactions help to sustain high metabolic rates supporting huge integrated organisms. These interactions help oxidation reduction cycles to be feasible and self-sustaining. The higher oxygen levels in Earth's atmosphere help oxidize low-carbon compounds, such as glucose, effectively extracting biologically beneficial energy. Concurrent with this process, photosynthesis replenishes the atmospheric oxygen supply and converts the carbon dioxide produced back into reduced carbon compounds for food. Any ecosystem aiming for significant size and complexity depends on comparable cycles, not just oxidation and reduction, even if those seem most likely. It is thought that oxygen reaching a critical atmospheric concentration was mostly responsible for the Cambrian explosion, which produced Earth's first significant life forms. About 15 degrees Celsius is Earth's mean surface temperature. This is much lower than the temperature at which most proteins denature, between 45 and 50 degrees Celsius, yet much higher than the freezing point, 0 degrees Celsius, of water. This value shows that most terrestrial environments, where liquid water is present, can be home to aquatic species. Physical restrictions on size do not limit organisms, since they can expand in terrestrial, aerial, and aquatic habitats. This limitation does not apply to life forms buried in ice inclusions or contained in soil. Seasonal thermal cycles help species suited to use extreme cold, extreme heat, and moderate temperatures all year long, and all fluctuations in between evolve. Increased complexity naturally results from the specialization of physical structures and organ systems. Life is essentially limited to temperatures within which its main solvent can remain liquid. Thermal habitats where water is the main solvent can cover the range of liquid water temperatures, from freezing to boiling. Between 0 degrees Celsius and 45 degrees Celsius, multicellular organisms flourish. Natural selection on Earth has produced a wide spectrum of adaptations over this temperature range. Microorganisms, known as extremophiles, live in the very extreme margins of environmental conditions. Many different adaptations produce an interesting range of organisms. Does a limited thermal range in solvents other than water prevent significant size and complexity? Not precisely, but theoretically the difficulties are more important. One imagines Titan's ethane and methane lakes' development of large benthic organisms. The limited thermal range in such an environment causes less degrees of freedom for developing different specializations. Although their precise nature is unknown, non-aqueous solvents have limited biochemical flexibility. Many species show mobility because of suitable temperatures and space availability which support dynamic activity. Microorganisms need sensory adaptations to organize incoming data and match it with existing motor commands. For terrestrial animals, this process has produced the evolution of nervous systems. Usually, larger complex organisms match with complex nervous systems. Mobility has biological uses in terms of prey pursuit, predator avoidance, mate locating, often requiring a sophisticated behavioral repertoire for mate recognition and copulation, resource distribution, and refuge seeking. Each choreography requires different anatomical and physiological adaptations to execute it. Earth's features fit for the development of big, sophisticated, and varied organisms, making it imperative to realize that life developed almost 2 billion years before reaching a macroscopic form. Representing the most basic cellular organization, it first lived as unicellular and prokaryotic for at least 1.5 billion years. After its potential was realized, life started immediately. Yet it stayed simple and homogeneous for more than half its existence. This pattern suggests that when life is perfectly adapted, it stays constant and unaltered. Our only experience of life lacks enough information to generalize the speed of life's emergence or the rate of its evolution and diversification under ideal conditions. Our single sample provides empirical data showing that even in ideal conditions, organisms could require large amounts of time to reach notable size or complexity. There is more possibility for diversification in the bigger and more complex the organism is. Still, if evolution takes time to produce major and complex organisms first, the whole evolution of a varied biosphere calls for even more time. Whether there are natural constraints on the biosphere's diversification rate is still unknown. The speed with which planetary conditions change determines the rate-limiting factor. Habitats can be classified based on topography, altitude, moisture, sunlight exposure, substrate, rock, soil, sand, or absence, air, water, either generally or in relation to prevailing or changing temperatures. Among the several biomes, polar, taiga, tundra, alpine, prairie, woodland, desert, and tropical forests show great habitat variation. Fractionation occurs from the community to the microhabitat on our highly differentiated planet. Where different habitats meet or change into one another, the gradients or interfaces create extra habitats. On planets like Earth, the interfaces span large bodies of liquid, water, and substrate, land. In contact at and beneath the surface, establishing new habitats at the junction of land and water, land and air, and water and air helps to increase biodiversity. Look at the variety of species found in coastal tidal pools, along riverbanks, and in the upper layers of a rainforest canopy. In places with more consistent temperature and topography, such as polar regions, biodiversity is much reduced. The sequence of organismal evolution, a relentless process, is influenced by a planet's or moon's geophysical history. If planetary history has been complex, the resulting biosphere will reflect historical variations. Earth's abundance of energy and mild temperature during the Mesozoic era helped reptiles, especially dinosaurs, to occupy and rule almost every ecological niche on land, in the air, and in the oceans. As global temperatures dropped and vegetation changed, homeothermic mammals and birds took over from the Mesozoic era's catastrophic end and the dinosaurs' extinction. As such, the most common vertebrates in Earth's biosphere are mammals, pre-adapted for homeothermy and internal gestation, and birds, pre-adapted for homeothermy and flight. They could have dominated Earth even without the event triggering the extinction of the dinosaurs. The ability to combine knowledge and foretell future results defines intelligence. As mobile life evolved, organisms that get their food by grazing, collecting, or capturing, their nervous systems or similar systems that help them work together and respond, may have become complex enough for intelligence to develop. Originally showing up in cephalopods over 400 million years ago, intelligence has independently evolved in several major animal groups on Earth. Still, it has not become a norm or a clear result of evolution. Technology is using tools, knowledge, materials, and energy by a living entity to improve its impact on the surroundings. Except for a few exceptions, only Homo sapiens have evolved significant earthly technological capacity. We investigate the necessary conditions for developing intelligence and technology and why these conditions might not be sufficient to generate any result. The infrequency of intelligence and technology developments accounts for this challenge. From a merely human perspective, intelligence is a complex phenomenon with notoriously difficult evaluation. Still, many famous examples of intelligence have surfaced over the course of Earth, along with at least one meta-intelligence incident. Examining these cases clarifies the important elements behind their emergence. Among all the invertebrates, cephalopods are the most intelligent. About 500 million years ago, in the late Cambrian period, they broke off from other mollusks. From octopuses, squids, cuttlefish, and a nautiloid surviving today, they proliferated and diversified in following eras until suffering a catastrophic decline during the Permian crisis 250 million years ago. Conversely, those forms are active benthic hunters and foragers. They have sophisticated motor systems allowing exact movement of their 8 to 10 appendages, highly developed tactile and visual senses, and sophisticated mouthpiece manipulation. Managed by a large brain composed of many parts, each with particular roles arranged in a logical manner, cephalopods have great coordination between their senses and movements. The brain marks 4 levels of control. Lower motor areas controlling particular unexpected movements, upper motor areas facilitating smooth movements, memory storage and sensory processing combining information from taste, smell, and sight, and brain areas involved in motivating and reward assessment. Employees who grasp octopus behavior assert to have observed 11 personality changes in animals subjected to surgery or injury on their subfrontal lobes. About 300 million years ago, insects diversified to occupy every ecological niche in the Carboniferous period coal forests. Social insects, including ants, wasps, and bees, had evolved from their ancestral forms about 150 million years ago. Although individual social insects are not thought to have intelligence in the conventional sense by biologists, They show traits implying intelligence is one thing. Notably, among fungal farming ants, they build complex habitats, assign tasks, communicate symbolically, as seen in bees, greatly change their microenvironment, raise food, domesticate other species, fight war, and cooperate for the good of all. Thus, they represent a kind of meta-intelligence. The success of social insects indicates that this type of intelligence helps them adapt. Thus, it is equally crucial to investigate the loss of these intelligent-like abilities, as it is to investigate individual intelligence. From flying reptiles during the late Cretaceous period, almost 70 million years ago, parrots and their cousins developed, while modern cockatoos first emerged some 20 million years ago. Macaws first arrived in the New World after the Andes developed some 28 million years ago. Renowned for their intelligence, the cetaciforms, parrots, macaws, and in some non-human primates. Their brain-to-body weight ratios can reach those of chimps. Most species show rather strong social activities. Over many dialects, the African grey parrot can pick up a vocabulary of several hundred words, linking words with meanings and grasping simple syntax. Though there is some disagreement about the degree of their cognitive capacity beyond imitation, this mimicry by itself shows notable intellectual capacity. Some birds show evidence of symbolic learning. Comprising crows, jays, and ravens, the friendly Corvidae family shows traits of causal thinking, adaptability, creativity, and planning reminiscent of chimpanzees. 5. Mammals in the order Cetacea include whales, dolphins, and porpoises. Near the beginning of the Cenozoic 65 million years ago, they most likely strayed from their terrestrial predecessors and became more amphibious, where ocean buoyancy allowed them to grow to be the biggest animals on Earth. Their brains are also the largest that have ever evolved. The blue whale's brain is 9 times the size of the human brain, 6. Cetacean brains, by the Miocene approximately 20 million years ago, had reached, essentially, their modern scale. Most of the brain growth in cetaceans shows a great elaboration of the neocortex outside the areas of sensory-motor primary projection. Once entirely marine, their remarkable dependence on hearing and the neural specializations for that sense evolved quickly. Other changes in the body have made it feasible to produce sounds, which has resulted in a complex echolocation system and a communication system whose whole intricacy is unknown. Their vocalizations are sophisticated. They seem to be able to identify and interact personally. They are good at learning and copying different vocal signals. 7. They are anticipatory and whimsical. They are unquestionably generous and quite gregarious. Field study data have even been taken as proof of dolphin cultural transmission. Among terrestrial animals, elephants have the biggest brains and neocortical capacity. Though usually considered intelligent, their performance on short-term cognitive tests, including demonstrations of cause-effect learning, is poor. In long-term spatio-temporal memory and complex social interactions, they shine. In mirror tests, they show self-awareness and increased sensitivity to dead or disabled friends. Early in the major mammalian radiation, at the beginning of the Cenozoic, roughly 65 million years ago, primates separated from ancestral insectivores. Separated from other primates about 40 million years ago, simian primates, which include monkeys and apes, started to evolve bigger brains. Roughly 16 million years ago, in the Middle Miocene, apes had evolved from Old World monkeys, and the common ancestor of chimpanzees and humans separated from ancestral gorillas. Humans separated from chimpanzees and started diversification into several species some 6 million years ago, by 4.4 million years ago. Attaining modern morphology and cranial capacity, Homo sapiens is the only surviving representative of several competing human lineages. The evolution of hominids showed a constant flow some 200,000 years ago. The expansion of the neocortex defines brain size most essentially, while the neocortical expansion in the cetacea most certainly exceeded that of humans 20 million years ago. The anthropoids experienced an evolutionary acceleration in brain size much more recently than the cetaceans. The human brain surpasses that of the chimpanzee within the last 6 million years. Tapuhi 10. For these two distantly related mammals, the acceleration of neural complexity has thus been an entirely independent occurrence. Cognitive and behavioral complexity clearly rises steadily over primate evolution. Monkeys began social grooming 30 million years ago. Orangutans learned to predict 16 million years ago. And gorillas exhibited creative behavior 7.5 million years ago. The chimpanzee human ancestor of 7.5 million years ago most likely had the social hierarchies and interactions, capacity for playfulness, altruism and dishonesty, and ability to form images and abstract ideas seen in modern forms, 12. Though the capacity for symbolic language must have been present, since modern chimpanzees can master a limited vocabulary and syntax with sign language, a full-blown symbolic vocal language evolved only in humans, probably less than 2 million years ago. Every example above reflects a different evolutionary event. The link among cephalopods, social insects, and vertebrates is unknown, and their cerebral structures show little resemblance. Mammals broke off from the reptile line with invertebrates, which would finally produce birds long before major intelligence emerged in either lineage. At least 40 million years ago, before brain expansion in either group sped forward, the last common ancestor of cetaceans and primates most certainly existed. Though their divergence occurred tens of millions of years before either lineage experienced the selective pressures resulting in amazing brain enlargement, elephants and cetaceans may share a closer relationship than primates. Different starting conditions led to different outcomes regarding brain enlargement and improved cognitive skills. Furthermore, it is noteworthy the frequency with which obvious intelligence has evolved. The groups do not show a consistent ecological theme covering marine, terrestrial, and arboreal flying environments. Thus, are there any other factors that especially help intelligence to evolve? Considered basic are the following elements. Shape. In all cases of individual intelligence, the animals displaying it usually have bigger body sizes than the typical for their taxonomic group. In this regard, cephalopods, whales, and elephants are especially important. It should be clear from this rule that meta are not covered. Degree of activity. More great sensory processing and motor control are required of an active lifestyle than a sedentary one. Active organisms move through a changing environment, which means they need to pay attention to things that inactive organisms don't face, like balance, speed, depth perception, telling what's in front from what's behind, recognizing features, like figuring out if something coming towards them is friendly or dangerous, knowing where they are, and remembering places and situations they've been in before. Moreover, this kind of exercise requires a system to control and coordinate muscle movements in a suitable sequence and intensity, hence calling for a different kind of learning. An animal's sensory input and motor control must be more sophisticated and exact the larger and faster it is. These elements propel the development of more neural components and their intercommunication. We consider this phenomenon to be cortical neural architecture. One common feature of intelligent animals is the enlargement of cortical brain structures. The arrangement of the cortex helps nerve cell columns at a high density to be vertically stacked easily. More neurons go along with more processing power. Another important feature of cortical architecture is its topographical mapping of the external surroundings, in which knowledge from a given external point is projected to a matching point in the brain. Mammals develop their cerebral cortex convoluted due to the fast expansion of cortical areas relative to brain volume. This feature lets a two-dimensional expanse of brain tissue show a more important count of environmental points. In terms of visual imaging, the process improves detail resolution, increasing the complexity of handled data. Higher intelligence is always correlated with complex sensory processing. Primate and cephalopod analysis of tactile and visual cues is remarkably accurate. Avian species show extraordinary acuity in both vision and auditory sense. Remarkably, parrots and primates have evolved in visually complex arboreal environments. Among vertebrates, marine mammals have among the best auditory capacities. Only bats probably match their echolocation sensitivity. The counterpart of high sensory resolution is fine motor control. Fine motor control is the counterpart of high sensory resolution. Controlling 8 arms, each combining delicate, sophisticated and complex mouth movements, challenges octopuses. The motor control of complex vocal apparatuses helps parrots to replicate sounds. Primates also have exact control over hand and finger motions, subtle muscle movements to regulate vocalization, particularly in humans, and multifarious facial expressions crucial in social interaction. For hominids, precise coordination of gross limb motions, like those for grasping and throwing objects, has also been a major adaptive benefit. From an arboreal life which promotes the development of grasping forearms and great eye-hand coordination and values depth perception and acuity, they evolved from. This would have favored combining visual inputs with other modalities and a matching expansion of associative areas of the neocortex. It would have also pre-adapted them for the grooming characteristic of primate social contacts. Social activities. Every example of an intelligent vertebrate discussed is highly social. This calls for sophisticated communication by facial expression, vocalization, or behavior. It usually means exact social memory and hierarchical and territorial awareness. Suitable social behavior thus depends on a great degree of learning, abstraction, high sensory acuity, and improved motor control. The hominid model shows quite nicely how sensory motor resolution interacts with cognition. According to a long-held belief, the ancestral apes, which finally developed into hominids, traveled from forest environments to the recently created savannas more than 20 million years ago during the early Miocene. Larger body sizes, partial upright posture, increased tool use, and the ability to hunt bigger prey on the plains would have heightened individuals' need for superior eye-hand coordination, a greater sense of time, more complex social structures and behaviors, and better coordination of group activities. Recent studies show that Ardipithecus ramidus, who lived in specific woodlands 4.4 million years ago, possessed 2 modern human features: bipedalism and reduced male canine size. The results suggest that reduced male aggression, food for sex interactions promoting monogamy, and the need for paternal investment in offspring during early hominid evolution could all be related to advanced cognition. Though rare among mammals, these social innovations could have helped to explain or cause the rising encephalization linked with higher intelligence. Still, as humans negotiated the Pleistocene ice ages, other hominids and each other presented competition. Their neocortex grew concurrently to support cultural development, better tool use, and language acquisition. Level of trophic growth. Usually, organisms at higher levels of the food web show more intelligence than their prey at lower levels. Generally speaking, carnivores have better ratios of brain mass to body mass than herbivores. The results suggest that catching prey requires more behavioral coordination and anticipation than avoiding predators. While planning, anticipation and learning demand more advanced, flexible neural circuitry, fear and instinct reflect more basic, ingrained neural functions. restricted to the order Hymenoptera, class Insecta, phylum Arthropoda. Most social insects are ants, wasps, and bees. Except for the termites, socializing has emerged independently in many lineages among this group, in no other insect order. This is ascribed to the evolution of haplodiploidy, whereby one sex has one set of chromosomes, haploid, and the other has two sets, diploid. In this sense, genetic variations define different roles that result in a caste division of work 3. This kind of arrangement results in a different repertory of behavior that seems to be rather rigid and instinctive. Although honeybees can transmit exact direction and distance, their communication system is rather stylized and apparently literal. Therefore, individual behavior does not exhibit any sign of the plasticity usually connected with intelligent behavior. Still, the whole effect of many people fulfilling various roles produces results that seem rather intelligent if done by one person. This case of meta-intelligence has astrobiological relevance, since it could be a different path for life to reach intelligent ends on another planet, without the need for evolving individual intelligence as we know it on Earth. Intelligence clearly confers a selective advantage and should thus be a preferred evolutionary result. In such a case, intelligence would be more common than it is right now. Clearly, life on Earth has shown constant progress in the evolution of increasingly intelligent organisms. Swordfish surpass jellyfish in intelligence. Reptiles show more amazing behavioral plasticity than amphibians. And primates are more intelligent than any representatives of the insectivores from which they evolved. Still, among most animals, few species in a given lineage show a qualitative intelligence boost. Most of the biomass on Earth comes from plants and bacteria. They lack intelligence completely. Our intuitive assumption must thus be mistaken. Among biological traits, intelligence is a recently developed quality of brain mass, neural architecture, and circuitry. The neocortex was first developed to control exact movements and process detailed sensory data, not only to enhance cognitive ability, but also to aid with intelligence. Natural selection could then favor the basic components of intelligence for their inherent worth once they were known. Look at the situation involving two mammals, the lion and the gazelle. Evolution has favored the development of a sizable brain with an enhanced forebrain for processing complex sensory data and sophisticated motor control in both species. Still, the outcomes differ for prey and predator. The gazelle has great sensitivity and agility, but less intelligence. The lion, although less nimble, shows more outstanding cognitive capacity as it hunts its prey. The question begs itself: why did intelligence evolve in lions, but not in gazelles? One partial explanation is that for survival, gazelles give speed top priority over intelligence. 11 out of 12 times, evasions of predators support this strategy. However, when several lions hunt together, their success decreases, since this behavior calls for more intelligence and coordination. Natural selection constantly balances several tactics, one for predation and another for escape, in the development of prey and predator. Based on different benefits, the choice goes for the gazelle's speed over intelligence and the lion's intelligence over speed. This evolutionary result shows that intelligence and speed have rather different benefits. Exists more to this problem. Is intelligence maladaptive in some particular situations? Lack of sufficient knowledge of intelligence and its underlying causes among neuroscientists makes a clear solution elusive. Effective information processing, integration, and learning require certain neural changes that might compromise other fundamental abilities. Furthermore, intelligence could lead to complexities. More simple behaviors and less complicated social structures usually improve group survival. These findings might help to explain why intelligence seems underused in some situations. Finally, intelligence could be self-limiting. This idea becomes clearer when one considers technology's consequences, which calls for creativity as a prerequisite. Two main reasons clearly show astrobiological relevance for the beginning and fate of technology. First, any thorough knowledge we could find about extraterrestrial life and any insights such life may provide about us will need advanced technology for detection, analysis, and finally, exploration of other worlds. Second, technology could greatly affect the path of its biological antecedents and successors, since it transcends biological limitations. The human species inhabiting Earth has greatly developed its technology. Since this is the only known occurrence in the universe, developing a broad theory about the sources of technology is, at best, challenging. Analyzing our particular technological development cannot help us to explain important elements. About 200,000 years ago, humans rapidly evolved a larger forebrain that improved areas of the brain connected to planning and thinking, while also helping them control their movements better for using tools and speaking. These developments resulted in the development of symbolic spoken language, improving interpersonal relationships in ever more complex ways, and supporting the founding of simple hunter-gatherer societies. The first departure from total servitude to environmental conditions was learning how to start and control fire. This invention gave people a concentrated and controllable energy source, warmth, improved diet by cooking, and protection against predators. It then would become an indispensable tool for manufacturing. The domestication of wild animals, especially dogs and several ungulates, probably marks the next major technological development. People had to learn the language, improve tools, and become masters of starting and controlling fire over the long term. They survived hunting and gathering. They learned a great deal about flora and fauna throughout the process, which finally helped them to be able to raise and propagate animals, so bringing about agriculture. Once agriculture became a basic feature of human life, people could create more than required. This excess helped to divide labor and finally led to social stratification, sophisticated cultural frameworks, and very orderly social interactions, collectively known as civilization. Dependent on the smelting of ores to create metallic artifacts, the development of civilization helped to build edifices and weapons. This knowledge enhanced the handcrafted goods derived from natural resources, including pottery, papermaking, textile manufacturing, and other objects. Humans started to control and affect their surroundings to a degree never seen in other species by using manufactured objects and domesticated animals. Thus, technology developed. Technology advanced thanks in part to mathematics. Originally impacting agriculture, it changed travel and navigation, turning ancient astrology into astronomy and requiring knowledge of geometry and many computational techniques. Once the usefulness of mathematics became clear, its application exploded almost everywhere involving physical manipulation. Mathematical accuracy in machine design, scientific knowledge of the natural world, and the use of new energy sources helped humanity to control their surroundings progressively. Though lacking complexity, scientists eventually created machines for computation, and computers sped information processing to a level that matched the human brain. The junction of computers and machines has resulted in the development of robotics, starting a path toward mechanical entities with some basic traits of living entities. The basis of intelligence, neural complexity, is only one of several requirements for technical progress. Creating and using technology calls for the capacity to consider several possibilities, visualize non-existing objects and project outcomes, and grasp numerical relationships. Still, at least three more elements have to show up if technology is to advance. Complex materials demand resources for fabrication and construction. In human settings, this comprised stone, wood, and animal products, including fur, gut, and bones. Eventually, the smelting and extraction of metal ores became absolutely vital, under control energy. The development of humanity and technology depended much on the control of fire. Beyond its purposes of providing partial autonomy from environmental elements and protection, metal smelting was absolutely essential. Other forms of controllable energy that provide the concentrated energy needed for manufacturing are machinery for harnessing wind and water power, and finally, electricity. Possess manual dexterity. On a planet like Earth, where materials and energy abound, an intelligent entity must precisely control these resources. This requires great manual dexterity, which appendages with individually controllable digits, such as fingers, help to enable. Analyzing the few cases of obvious intelligence evolution helps one understand technical development's rarity. Two of our specimens relate to aquatic life. Though they lack manual dexterity, cetaceans, whales, and dolphins show great intelligence, remarkable sensory ability, and sophisticated communication skills. Sophisticated nervous systems and manual dexterity define cephalopods, octopuses, and squids. Even if cephalopods were intelligent enough for sophisticated thinking and cetaceans could handle objects, it is still doubtful if they could locate the required elements to create tools and machinery in a generally similar ocean environment. Another difficulty is the acquisition of under-control, concentrated energy. Underwater use of fire is impossible. Hydrothermal vents are neither portable nor controllable, even though they offer focusing thermal energy. Therefore, the marine environment still challenges technological development after 4 billion years of evolution. Though among brilliant animals, only primates have the manual dexterity needed for the exact manipulation of objects and materials, the terrestrial environment provides material complexity. With their beaks, parrots show excellent fine manipulative ability. Elephants show great trunk dexterity. However, neither species can do the micro-manipulation needed to thread a needle. Primates' limb structure, which allows them to throw stones or spears, could also be a vital means of object manipulation, indicating a significant competitive advantage. The example of meta-intelligence is striking, since social insects build rather sophisticated constructions, including intricate termite mounds and honeycombs. These insects imply the possibility of collective meta-intelligence, even though each one of them is smaller than those displaying individual intelligence. The lack of sophisticated, adaptable technology in these meta-intelligent species could indicate that intelligence has not been essential for survival in many species. If meta-intelligent life forms satisfy other criteria, then it would be premature to say that they cannot evolve technology. Enrico Fermi, the eminent nuclear physicist, suddenly asked, "Where are they?" while having coffee with his colleagues in Los Alamos, New Mexico. When asked to explain, he said, "If technologically advanced aliens exist, why have they not visited Earth? Or if they have, why is there no awareness of their presence?" Therefore, the paradox connected with Fermi suggests that, although there is no evidence to support this, based on statistical reasoning, aliens with sufficiently advanced technology should exist. Should they exist, would they not have the means to be conscious of life on Earth and show themselves to us by now? Many theories have been offered to explain the Fermi paradox. Stephen Webb especially suggested solutions, none convincing enough to stop him from concluding that extraterrestrial civilizations certainly do not exist. This pessimism is unwarranted. Still, I agree that the paradox is real. We note the following, even though we are not ready to offer a definitive answer. According to statistical data, there is little chance of encountering extraterrestrial intelligent life, ET, Our argument is predicated on the idea that the likelihood of contact results from multiplying several low-probability factors. We also expect a broad dispersion of current extraterrestrial intelligence, ETIs, simultaneously. 20 light-years from our solar system house, almost 130 stars. Unless the probability that one of these stars hosts planetary bodies with an ETI exceeds 1 over 130, statistical analysis reveals that the closest ETI is at least 20 light-years away. Should stars retain their density from our Sun in a flat plane extending to 100 light-years, the probability must exceed 132,500 to predict an ETI within that range. Even if these chances seem rather favorable for the presence of another ETI, 100 light-years still is a great distance. Should an extraterrestrial intelligence, ETI, be located 100 light-years from Earth, its antennas could detect the first human-generated radio signals, which are just 1 century old. On another world is just now entering the time window within which they can detect us, if they are depending on radio transmissions of clearly technological origin. Still, they have known about us by some other long enough to beam an electronic signal straight at us. Only, for roughly 100 years, have we been able to personally detect such signals. Suppose they chose to show up, and could thus. No living being would know what to make of them, unless they timed their landing within the past 2 or 3 million years, when humans smart enough, maybe, to distinguish them from flying birds would have been present. They could plop down in the middle of the Rift Valley of Kenya in spaceships lit by flashing neon lights. Should they have settled in central Kansas, they would have had to do so within the past 10,000 years in order to be recognized. Considering that life has existed on Earth for at least 3.5 billion years, and may have existed far longer on the planet from which the ETI mission was launched, hitting exactly the time window of 2 million years, or 10,000 years. 0.06% and 0.0003% of life's existence, respectively, would be highly improbable. Communicability. Should an extraterrestrial intelligence unintentionally find Earth's physical presence or detect interesting electronic signals from our far-off universe region, these alien observers have to be able to decipher the data and determine it as originating from a type of life. Identification of technological data from space calls for a clear language. Although they may not appeal to other intelligence, the plaques and recordings sent into space with our spacecraft reflect general approaches to providing information understandable to our cognition. Though aware of our existence, an alien intelligence, ETI, might have chosen not to visit us for a number of reasons. Should its technology surpass ours, it could view us as little of a target of interest as ant colonies do. Human history on Earth shows that historical predecessors imply that interactions between intelligent entities of different backgrounds usually result negatively for the technologically inferior species. Moreover, if our possible guests have similar organic chemistry, they could understand the danger of infectious diseases for both of us. People do not show any hesitation in approaching extraterrestrial life. Usually, our natural curiosity has been of advantage. Along with our developed cognitive skills, it has helped us to quickly absorb information about our surroundings and change our behavior. Still, in this context, this interest could be reckless and dangerous. Any extraterrestrial intelligence able to reach us soon will have much better technology. At best, we will have little control over the situation. If our future guests are kindly inclined, they realize it is best to keep our ignorance of their existence. We usually suggest one of 2 readings of this position. The first claims that although extraterrestrial entities have visited us in the past and still do so sporadically, they keep a distance and avoid direct interaction for different reasons. According to a different reading, extraterrestrial intelligence has made contact via other unusual events, such as animal mutilations and human abduction, among other channels. According to the second view, extraterrestrial entities coexist with us under the cover of regular humans or other life forms. The idea that extraterrestrial life has visited Earth in the past and is still present is strengthened by a never-ending flood of reports about unidentified flying objects, UFOs, and historical events connected with them. Usually, thorough research can adequately explain the great majority of UFOs. Furthermore, no concrete proof of UFO spacecraft or traces of alien life forms has been presented. This is a fact generally accepted by the scientific community ready to support such conclusions. Thus, even if the idea of UFOs as actual alien spacecraft, either sent by or carrying extraterrestrial intelligence, generates great excitement, it must remain a theory until objective evidence reaches a significant scientific agreement. With or without auditory emissions, the traits ascribed to UFOs match those of advanced spacecraft. They show unusual or unidentifiable forms, can hover easily, and accelerate at physically implausible velocities. Such data makes us less prone to completely discount the idea of extraterrestrial visits. According to the other view of the idea of extraterrestrial visitation, aliens live among us, indistinguishable from other life forms, including humans. Men in Black look at this idea via artistic expression and comedy. Unless they share our irrational curiosity, no biological or mechanical relic suggestive of the presence of these. Extraterrestrial entities has been found despite their challenge of intention identification. Although supporters of this theory show great fervent enthusiasm, there is no supporting data to indicate that aliens, with higher intelligence and technology, would rather fit into humanity than destroy or exploit us. Though only hypothetical, it is reasonable that technology is intrinsically self-limiting and unable to support discovery. Any extraterrestrial intelligence that develops technologically most certainly results in its own quick death. This event might arise from rendering its home planet uninhabitable before survivors can colonize another planet, or from the technological capacity for competition and destruction, surpassing the capacity of natural selection or programmed evolution to control such destructive tendencies. Though this is usually true, the counter-argument holds that exceptions must exist somewhere in the great universe. Although this presumption is fair, it ignores the improbabilities described in section 12.4.1. Indeed, if technology is mostly self-limiting, this limits the lifetime of a conscious and technologically competent life form to interact with extraterrestrial entities. Argument by analogy. The fate and discovery of the Hawaiian Islands between 0.5 and 5 million years ago. The main Hawaiian Islands sprang from a volcanic hotspot in the Pacific Ocean. The most modern, the Big Island of Hawaii, first appeared 500,000 years ago. Through immigrant species, life gradually settled on the island and developed in isolation along a unique path. Arriving probably between 300 and 500 BCE, humans brought a species able to establish a Stone Age civilization that has lasted to this day. Long before people arrived in Hawaii, civilization had spread over most of the world and attained a technological and social sophistication in the Eastern Hemisphere much above that of the Hawaiian Islanders. No one from the advanced Eastern countries made contact with the people of Hawaii until 1778. The Hawaiians thought theirs was the only form of intelligence existing on the planet as of 1777. Hawaii's isolation and small scale delayed its discovery by a technologically developed civilization until 2,000 years after human habitation and 500,000 years following ocean emergence. The East had evolved to the Iron Age, when a Stone Age civilization emerged in Hawaii. Still, 2,000 years would pass before interaction occurred, 600 years after Eastern Hemisphere open ocean navigation began. The initial interactions between Hawaiians and Europeans were positive but fleeting. Conflict soon started, exacerbated by native inter-island warfare and European diseases wiping off the native population. Settlers from Europe, Asia, and North America essentially took over the islands from the native people within a century, bringing foreign culture and technology. For 2 millennia, the remoteness of the Hawaiians shielded them from technologically advanced attackers, since they could not advertise their presence across the vast Pacific Ocean. Once found, they went quickly. The history of life on Earth suggests that particular elements encourage a net increase in the size and complexity of individual organisms across time. These elements cover a plentiful energy supply, temperatures fit for life on the surface and in the atmosphere, large liquid volumes, a mobile lifestyle, and enough evolutionary time. Moreover, environments marked by widely distributed habitats, regular seasonal and global temperature fluctuations, long evolutionary times, and complex planetary history are more likely to produce biodiversity. Though conspicuous intelligence has seldom emerged, with cephalopods, marine mammals, select avians, elephants, and primates as the main exemplars, ability has independently evolved many times on Earth. While lacking individual intelligence, social insects show amazing meta-intelligence in group behavior. Intelligence has evolved thanks largely to factors including great size, an active lifestyle, pre-adapted anatomical structures of nematodes, improved sensory resolution, refined motor control, and complex social interactions. Though insufficient for technological development, cognitive ability is indispensable. Besides cognitive capacity, an intelligent entity must have manual dexterity, access to concentrated and under-controllable energy sources, and appropriate material resources. The vastness of space and the great length of time separating intelligent, technologically advanced civilizations reduce their chances of meeting another such civilization, even if they are inclined to explore outside their home planets. Thus, the inability of humans to interact with or be contacted by extraterrestrial intelligences, neither surprising nor evidence of their non-existence. The solar system has existed for almost 1/3 of our 1.37 billion-year material universe. Life clearly has probably evolved longer here than in other corners of the universe. Has it continued and still exists? Any given situation or context calls for a bifurcated response based on this dual search. First, we determine whether life could have started and evolved, under which circumstances. Second, we have to ask about its circumstances and possible length of existence. The first issue has taken the front stage in the past documentaries, not only because of its fascinating character, but also because it has practical consequences for our expected lifetime and the circumstances surrounding our final death. Once they have sufficiently evolved from their ancestors to be judged unique, the theory holds that all living forms will vary in one of 3 directions. 1. The historical account of life on Earth supports this view. First, new kinds of organisms typically show up fast in terms of geological time, develop the best features for their habitats, and then reach a stage where their shape and function stay mostly the same for a long time due to stabilizing selection. Most species will eventually go extinct, since the biotic or abiotic environment changes faster than the organism can adapt. Rarely, a group of organisms may develop a very advantageous adaptation that results in a significant change, producing a whole new set of descendants that flourish in the new possibilities presented by environmental or evolutionary changes. Most life exists in a plateau phase of development at any moment. This occurs since, in an environment where the environment remains the same, stabilizing selection is more common than directional selection, and emphasizes maintaining organisms' current features instead of changing them. Important changes in the surface of the Earth usually happen slowly, including changes in landforms and climate. Unless disturbed, ecosystems usually find a steady equilibrium or predictable cycles. For species, the physical and biological traits of the surroundings remain rather constant in the short run, yet they vary for individuals. This information suggests that any mutations or evolutionary mechanisms changing the adaptations of organisms to their surroundings are selected. Extended changes in surroundings and ecosystems call for either adaptation or confrontation with extinction. Still, many cases of lives remain essentially unaltered over long periods. The most conspicuous example is the microorganisms, retaining the same simple unicellular structure as their ancestors. The archaea and eubacteria are the two primordial life forms on Earth. Though fundamentally, they remain somewhat different from their form at least 3.5 billion years ago. Bacteria are always changing to avoid new drugs or mutant threats. Since they live in rather stable surroundings despite the evolution of their hosts, parasitic forms are particularly prone to the plateau scenario. Giardia is one of the parasitic cells known as diplomonads. These have two nuclei that cause diarrhea by invading vertebrate digestive systems. Since they developed from prokaryotes to primitive eukaryotes, they have hardly changed. For almost 2 billion years, cyanobacterial progeny of the original photosynthetic organisms have maintained their simple bacterial form and function. Among the first terrestrial organisms in the plant kingdom, bryophytes, mosses, continue to cover the floor of our cool, moist forests after 360 million years. Among invertebrates, flatworms like planaria, arthropods like the horseshoe crab, and mollusks like the nautilus stand out for their amazing success and consistent form. From their arrival 400 million years ago, sharks have not fundamentally changed their form, behavior, or physiology among vertebrates. Turtles' appropriate defensive shape has stayed the same for 200 million years. Though convincing examples of biological resilience are mentioned above, most species eventually face extinction. Perfect adaptations are essentially permanent. Environmental changes or disasters cannot quickly enough apply corrections. One species disappears at a time, as extinctions happen constantly. Many biologists contend that with more species disappearing than arising through evolution, Earth is experiencing a major extinction event. We merely need to cite several of the more notable and amazing extinctions in Earth's biological past to more powerfully show our perspective. Early in animal evolution, a group of organisms known as the Ediacaran fauna experimented with several body forms. More competitive and stable body types, including arthropods, bivalve mollusks, and finally, vertebrates, which would rule the animal kingdom, replaced the experimental forms during the Cambrian explosion 540 million years ago. Placoderms, armored fish, dominated the oceans in the Devonian period. But their more nimble, unarmored progeny replaced them by the end of that age. Two major extinctions occurred 251 million and 65 million years ago, most likely caused by a natural disaster during the Paleozoic to the Mesozoic era. The first event eliminated over 80% of all animal life. Considered to have resulted from the collision of a large meteor at the Cretaceous-Tertiary boundary, the second event caused the quick extinction of dinosaurs and many other important terrestrial and marine taxa. Sometimes tragedies and hardships inspire radical creativity. The small, mostly nocturnal mammals were excluded from daytime habitats for the 150 million years during which dinosaurs dominated the Earth, so requiring the development of homeothermy, the capacity to sustain a high, stable internal temperature, to remain sufficiently active for foraging in the safety of night. After the extinction of the dinosaurs, this creativity helped to enable the later notable evolutionary diversification. Fish with air bladders, which improve buoyancy in water, developed lungs as a pre-adaptation when lungfish started traveling through the air between desiccated pools. Because they could access much more oxygen in the air than in water, the evolution of lungs gave amphibians and their descendants a new way of life. Other inventions have surfaced more slowly but have just as significant an impact. As their anterior gill arches grew ever more enlarged and became more articulated, jawless, filter-feeding fish developed into powerful predators. This meant changes in their muscles and nervous systems to control and synchronize a more dynamic lifestyle and a bigger body. Feather development, probably for thermoregulation, and changes in limb form turned arms into wings, enabling the flight of birds from their reptile forebears. In every case, jawed fish, air-breathing organisms, and flying reptiles, shifting to a different way of life, produced a huge diversity of offspring that filled new environments and ways of life. Our inadequate knowledge of life's adaptability, especially the extent to which it can flourish in conditions different from those on Earth, greatly limits our ability to estimate the degree of biodiversity in our solar system and beyond. Significantly consequential is the possibility for life to be based on elements other than carbon, using solvents different from water, and obtaining energy from sources outside light and chemical reactions. We investigated the advantageous traits of aquatic, light-driven, and some chemically supported, carbon-based organisms. The variety and complexity of Earth's biosphere match theoretical projections. Perhaps life cannot exist in any other way. This scenario is familiar since it reflects a biochemical basis for life comparable to what we know now. This situation will clearly restrict life to places where carbon-based materials, liquid water, the right amount of light, and chemical energy are available. We have often said that different materials, liquids, and energy sources could support life forms that we have never seen before. We shall refer to this situation as an exotic scenario since it involves life forms with biochemistry that is totally alien to human experience. It increases the spectrum of surroundings in which life can start and survive. Diversity of the solar system within the conventional paradigm. Should one believe that life can only flourish in aqueous settings made of carbon-based polymers? It should have emerged early in the developmental epochs of Venus, Earth, Mars, Europa, and possibly some of the larger icy moons such as Ganymede, Enceladus, Titania, and Triton. Thus, the extreme coldness of a habitat would have caused life to vanish. Only microbial sulfuric acid droplets found in the clouds can survive on Venus. Nowadays, Earth satisfies all requirements for developing big, sophisticated organisms and maintaining a vast microbial biosphere, including those fit for the evolution of intelligence and technology. The remaining planets must be sequestered below the surface, since they still allow some biospheres under the known conditions. On Mars, the soil or caverns would greatly limit mobility. The lack of significant energy sources will probably limit any surviving life on Mars to small, mostly stationary, mostly microbial forms. Though only under the surface ice layer, life may exist in the known conditions on Europa and possibly 2 or 3 more larger icy satellites. If there is enough energy to maintain the ecosystem supporting big, sophisticated forms, then significant amounts of liquid water would not stop organisms from developing into such forms. Considering the most unusual conditions for life in solvents other than water, extremely frigid moons like Titan and Triton may have living entities even in the present era. Organic compounds are rather common. Thus, we expect Titan's chemical constituents to be carbon-based. On Triton, silane polymers could create complex chemical building blocks in liquid nitrogen. In both cases, all living entities have to exist beneath the surface. Without knowledge of their liquid reservoir's volume and biochemistry, speculating on the size and complexity of possible life forms that evolved beneath Titan and Triton is difficult. Any life form cannot have great mobility given the extreme cold, so it seems unlikely that intelligence can develop because of the extreme cold, making Earth the only planet in the solar system that we think could support intelligent life, even in unusual situations. Also, our ability to guess where else life might exist in the solar system is limited because we don't know enough about how our solar system compares to others. Though our solar system has several examples of what will probably be found elsewhere, this may not be as severe as it first seems. We have terrestrial planets near the Sun, gas giants in more far-off orbits, greenhouse environments, cold deserts, airless celestial bodies, turbulent volcanic moons, varied atmospheric compositions, hydrocarbon plains and petrolakes. We also have captured satellites in improper orbits. Our sample does not include any type of planet. The only one absent is the gas giant circling close to its central star. These are well known to exist since most exoplanets found thus far match these criteria. Although no such planet is close by, using this book's ideas helps us deduce its features and evaluate whether it could support life. Since these are the areas where water can exist in liquid form, the habitable zone is sometimes defined as the range of distances from a central star where worlds might sustain life. The implicit assumption is that water has to be in a fluid form on the surface. The habitable zone could define the spectrum of Earth-like planet existence or past. Underlying the surfaces of celestial bodies, our solar system shows that water can exist as a liquid or liquid solution, depending on the presence of internal energy sources. Thus, we find the habitable zone to be rather useless. In the past film, we maintained that areas with broken-up habitats, where life can flourish on the surface, are more likely to produce complex ecosystems supporting big and intricate life forms. In such a sense, a habitable zone, perhaps renamed as a zone of macrobiotic complexity, would be justified. Our solar system usually consists of many planets and moons where liquid water can exist, although only under conditions that prevent the development of big and sophisticated organisms. There are rare appropriate conditions and historical settings that would help advance intelligence and technology. If these presumptions hold true, water-based life could be rather common. Large, sophisticated organisms would be rare, and intelligent life would be rare as well. Within the framework of exotic scenarios, the habitable zone idea is even less useful since it would change depending on the features of the life forms and would vary with every special combination of conditions. Every planet in our solar system, plus most of its major satellites, could meet the requirements for either the carbon-based, water-dependent life forms we know of, or unusual life forms yet to be found. Mercury and our moon could thus be excluded. Under the exotic scenario, we have to conclude that life in the universe is ubiquitous, considering the above assumption. We do not suggest that any solar system has to have some life. Planetary history and other elements may often prevent the beginning and survival of life, even in exotic conditions. The vastness of the universe has to include many worlds conducive to life. Though rare in percentage terms among worlds able for life, the total count of such worlds is probably rather large. Estimating the ratio of worlds where life would be regarded as exotic rather than familiar from our perspective presents more difficulty. More than half of the planets either have or could have had liquid water, implying that life or its traces would be familiar to us if our solar system is representative. Still, we cannot prove our solar system is representative. Our presumption of the ubiquity of life in the universe must be adjusted, considering the rarity of worlds where water can act as a solvent, and the absence of such exotic scenarios. This exercise starts with juxtaposing two models of life on any planet. The first model was the rare Earth model, which Peter Ward and David Brownlee, 3, most eloquently and successfully presented in their eponymous book. This model suggests that the rare and non-often occurring conditions necessary for carbon-based, water-dependent life to flourish on a planet like Earth cause complex macroorganisms to evolve seldom. Earth-like planets are thus rare, as is the kind of life that has evolved on Earth. The rare Earth model calls for the familiar scenario that we know. Ward and Brownlee argued for the rare Earth model, but also agreed that microbial sequestered life might be rather common. We have developed this alternative yet compatible model as life unseen. Together, the rare Earth and life unseen models capture the core of life everywhere. Given the constraints of the rare Earth hypothesis, it is almost unthinkable that clearly intelligent, technologically advanced life forms have not evolved elsewhere in the universe. On the other hand, such an event has probably happened several times in different places. Eventually, life on Earth will stop as the dying remains of an enlarged sun envelop the planet in the last phases of its natural existence cycle. Hydrogen fusion into helium at its core gradually increases the density, mass per volume, of any star of like mass to our Sun, producing a more intense luminosity. Every billion years, the Sun's energy output increases by about 10%. As planetary bodies and their satellites progressively distance themselves from the Sun, this data shows they must withstand enormous heat and radiation. The Sun will exhaust the hydrogen fuel in its core in around 5 billion years. Gravitational forces will cause the core to collapse to temperature for helium fusion into carbon and oxygen. Its environment simultaneously destabilizes and expands, turning the Sun into a massive red giant star. At the core, an inert accumulation of carbon and oxygen develops as the helium supply runs low. The star then sheds its outer layers in concentric shells, producing a core that becomes a remnant white dwarf. A dense, hot star, roughly the size of Earth, composed of carbon and oxygen, which has exhausted its fusion fuel sources. The Sun will then progressively fade, its light growing until it finally vanishes. Mercury, Venus, and maybe Earth will be swallowed as the red giant Sun grows to be more than 100 times its original mass. As Earth follows a path like Venus, it will become uninhabitable in about 5 billion years, resulting in a runaway greenhouse effect. How might the biosphere change before that event? There is no basis to assume that the broad results of plateau, extinction, and transition described in section 13.1 will not endure as long as Earth's conditions allow for life. While birds seem to be growing in number, mammals, reptiles, and amphibians are suffering a notable loss in biodiversity. While soil-dwelling roundworms maintain a notable but subtle advantage in biomass among organisms above the microbial level, invertebrates, mostly insects, rule the spectrum of biodiversity. While some species will become extinct as the temperature gradually changes, and a limited number of new species will develop, most groups of organisms will probably survive. Plants respond rather sensitively to temperature, moisture, nutrients, and animal dispersal agents. They will thus either adapt to or oppose changes in local climate, fauna, and their parasite count. Right now, in Earth's biological history, technological human intervention is starting to have a major impact. Plants will progressively change under the influence of genetically modified organisms. Domesticated animals may also experience similar changes. We anticipate genetic modification, direct gene addition or removal combined with selective breeding, to change populations of domesticated animals to fit human tastes. These hereditary changes can happen quickly, improving the survival of animals preferred by humans outside the range where natural selection might have led to their extinction. The evolutionary path of particular species will be shaped by human intention as much as by technology. Later on, this directed selection will mix with Darwinian evolution and become a major determinant of the fate of different species. In some species, such as humans and domesticated plants and animals, deliberate selection will predominate their evolution. Changes in one species can impact others. So when we intentionally select certain traits, It might also influence larger areas of the environment. Additionally, advancements in robotics will lead to the creation of more advanced and lifelike machines that could threaten or take the place of living beings, including humans. People will find changing important temperature features easier, intentionally or otherwise. 4. This suggests that the biosphere will be more greatly shaped by humans. The future and fate of humanity call for an analysis of the concurrent development of people and technologies. Synthetic components, including prosthetic limbs, pacemakers, and hearing aids, can improve the human body thanks to biomedical technology. Advanced computerized mechanical devices help stroke victims with mobility, assist the paralyzed, and provide vision for the blind by enhancing communication. From the beginning of tool use, humans have been natural-born cyborgs, co-evolving with mechanical tools to improve their capacity to control their environment. Thus, the fate of humanity is inextricably entwined with that of its auxiliary tools and machines. Humans might one day move from organic entities enhanced by mechanical means to mechanical entities with organic traces. We will separate the possible mechanical successors from the destiny of humans as organic entities to guarantee clarity. Peter Ward shows doubt about the likelihood of a disaster wiping out human life, attributing these possibilities to humanity's ability to protect itself from harmful conditions that might endanger other life forms free from technological protection. 6. Although humans lack extraordinary physical ability, they have different physiological needs, including homeostasis, a high metabolic rate, and prolonged internal gestation, making them quite vulnerable to major changes in temperature. Human survival depends on the capacity to protect oneself from gradually hostile surroundings. In the case of catastrophic events or cataclysmic changes, this calls for isolation in fortified buildings or underground spaces, where the main difficulty is keeping an energy source for food production. Ultimately, could view the challenge of biological survival on Earth as too expensive or dangerous. Thus, emigration to another planet becomes a desirable substitute. Notwithstanding great obstacles, humans could design and control an artificial environment, terraforming their new planet to meet their biological needs. However, in another world, the disease may present an ongoing challenge of an uncertain scale for humanity as an organic entity. Presuming bacteria will reduce in response to any threat less than sterilizing temperatures or planetary annihilation is not supported, though vaccination and a century of pharmaceutical development have greatly helped to combat infectious diseases over the past 2 centuries. The threat of a worldwide pandemic able to wipe off the human population still exists. Mechanical devices will probably help with cardiovascular diseases. A cure for cancer and neurodegenerative diseases is still elusive. An increasing list of carcinogens and unknown causes could help to explain why these diseases remain major concerns to human health. The change to a mechanical life form offers a feasible substitute for stopping biological degradation and disease. Whether living machines or non-sentient robots, mechanical entities, that is, cohesive, defined individuals able to maintain their structure and function by absorbing energy from their surroundings, may be designed. After creating self-replicating copies from basic elements, they would meet all our standards for life. This allows us to discuss mechanical life, which has a number of advantages over organic life. They would be resilient, energy efficient, disease-free, less vulnerable to environmental disturbances, and so less prone to, apart from their control and cognitive systems. They could be fixed with more ease, controlled with more accuracy, tailored to a higher degree, either turned off or kept active endlessly. From the natural or artificial selection point of view, particular traits could be highly valued even if they might not seem beneficial from a modern human perspective. Under such conditions, at what point would mechanical humans outperform organic humans in fitness, and what effects would follow for the latter? In the short term, robots have great potential to improve technological capacity, which drives natural humans to hasten their creation and implementation. There is no cause to doubt that their sophistication will continue to advance, making them ever more flexible and ubiquitous. Whether their cognitive capacity can match those of more intelligent species is controversial. While brains and computers approach problem-solving differently, there seems to be no reason to stop computers from reaching sufficient intelligence to program expectations and intentions. At that point, one's organic or mechanical perspective may not matter much. Should robots reach human-level intelligence and self-replication, they could claim ecological niche as humans, posing direct competition. Considered generally as complete competitors cannot coexist. The competitive exclusion principle is a well-established theory in biology. Imagine two organisms occupying the same ecological niche. Natural selection will favor one organism over the other. Hence, either the less favored organism will die or adapt to a new environmental niche. Robots may be built by their creators to remain perpetually subservient, for example, by ensuring they are sterile or incapable of self-replication, or sufficiently distinct to prevent competition with humans before reaching true competitiveness with humans. However, technological and historical patterns suggest that robots will become more intelligent, competent, and sophisticated. In such a case, a change from organic to mechanical life forms could occur in the domain now occupied by the only species that greatly affects its surroundings by technological means. Insects are the organic life forms most likely to disappear from Earth, whether humans survive as biological entities or create mechanical substitutes. More than any other life form, almost 1 million insect species are known. Estimates point to a 10-fold more significant count. Including freshwater habitats, they occupy every terrestrial niche. Though several species call the ocean home, their arthropod cousins, the crustaceans, shrimp, crabs, and lobsters, predominate in the marine environment. Documented from the early Devonian period, insects have existed roughly 400 million years ago. They grew into the many niches the spread of the Carboniferous forests 350 million years ago produced. Their resilience comes from their strong exoskeleton, articulated appendages, small-scale mobility, multi-stage life cycle, and fast reproductive capacity. They have survived at least 2 world disasters and remain impervious to all human technological development, including the most powerful poisons. Given the enormous variety their evolution over 400 million years generates, they will probably adapt to face the challenges presented by a planet in crisis, and continue until almost all life disappears. Marine life will probably remain mostly in a plateau state if photosynthetic producers remain viable to maintain the food chain. Individual changes can happen naturally, but major chemical changes in the oceans or atmosphere would rule out this possibility. Major crises like the Permian-Triassic boundary event, wiping off most modern animal species, can cause massive extinction. Still, we expect leaders of the main factions to stick to their beliefs as they did in the past. While mollusks have existed since the early Cambrian period, almost 540 million years ago, fish have occupied the ocean for more than 400 million years. Until the oceans evaporate, we anticipate bony fish, bivalve mollusks, such as oysters, and probably crustaceans to endure. According to Peter Ward's projection of animal life's future, the main terrestrial vertebrates most likely to survive the continuing mass extinction will be humans, domesticated animals, small cohabiting species, and birds. Thanks to technological developments allowing them to survive all but the most extreme environmental conditions, domesticated animals will endure. The vertebrate equivalents of insects are birds. Their success depends on their diversity and adaptability. ensuring that plants continue at the base of their food chain. Plants will adapt, as they have always done, to changing circumstances. As the sun ages, its energy source will only become more plentiful. The continental land masses will progressively become arid, retaining moisture only at the poles, and finally even that will be lost as the planet undergoes notable warming and freshwater resources Swedish. All animal and fungal species will die upon the extinction of terrestrial plants. Microbes will migrate beneath where they can survive for as long as they can retain moisture and generate food using other means than photosynthesis. Beginning over 500 million years ago, multicellular organisms flourished on Earth and merged into the microbial biosphere for at least 3 billion years, producing the most diverse solar system life. Resilience and great variety in life on Earth helped it to withstand several world disasters and consecutive ice ages. Under Darwinian evolution, taxonomically varied groups, including insects, mollusks, birds, and fish, will probably have some representatives as long as plant life exists, and the planet remains livable. Humans, their descendants or mechanical successors, and some carefully chosen domesticated species under their protection may survive until the Earth turns uninhabitable, unless they leave first using technology. It is quite difficult to project the look of the biosphere as it approaches a critical survival threshold. Currently going through a period of extinction, mostly driven by humans' quest for technological supremacy over the environment and its fate. Genetic engineering is changing the course of evolution by means of deliberate selection. This trend is expected to last and produce quite erratic and maybe unexpected results. By means of the historical trajectory and destiny of life on Earth as a paradigm, we can extend the fate of life in other environments. Upon its inception, life will adjust with the least change to the current planetary conditions. Once those conditions change, the evolution engine will alter the biosphere. More kinds of living entities will be created by big changes in habitats and diverse environments supporting water-based chemistry, so increasing the chances that some life forms will survive as long as the Earth exists. The number of survivors will drop as conditions grow ever more limited. In the presence of environmental stability, some life, though not particularly diverse, will survive even if it is quite demanding and limiting. In settings for intelligence and technology, one can change or minimize natural climate paths and handle other natural disasters. One should appreciate the possibility of moving from organic to mechanical life forms. When entities in such a world develop the capacity to travel across space, leaving for another world becomes a reasonable choice for mechanical and organic entities with the required means. When it first starts, life shows incredible tenacity and resilience. In the short run, stabilizing selection rules over directional selection to preserve organisms best fit for their habitats. Most life forms exist in a plateau phase of evolution at any one moment. In the long term, as environments change or disasters strike, evolutionary processes cannot react quickly to the altered conditions, which causes extinction. In rare cases, new discoveries or environmental changes can greatly enhance a previously unnoticed quality. Such events can set a new benchmark from which descended forms can develop and cause a major change in evolution. Although the whole spectrum of these worlds is unknown, our solar system provides a wide range of celestial bodies most likely found in any solar system. It should, we hope, be a useful surrogate for the probability of extraterrestrial life in the cosmos. Aqueous, carbon-based life forms have unique biochemical and physicochemical advantages over other building blocks and solvents. Assuming conservatively that this is the only feasible form of life, we would expect to find life, or evidence of former life, on at least 3 of the 4 terrestrial planets, Venus, Earth, and Mars, and on at least 3 of the 4 gas giants, Jupiter, Saturn, and Uranus. We thus conclude that both modern and historical life has been rather common. Under this conservative view, we can be sure that complicated macroorganisms evolved once only. They might have lived on Earth, Venus, and Mars at one point, but they are most likely extinct and limited to subterranean reservoirs on Mars. A complex ecosystem could be present underneath the surface of icy satellites. Specifically, Europa and maybe Enceladus are the planets under question. Regardless of their size or complexity, organisms today are totally apart from every other celestial body in our solar system, notwithstanding their past. Should a more permissive assumption be adopted regarding the conditions favorable to the emergence of life, the exotic scenario? The potential worlds currently existing within our solar system must be extended to encompass Titan and Triton. This scenario extends the range of possible habitats for life across the universe, but it does not change the fundamental reality that most of the time, life will be limited to subsurface environments and is probably small or microbial in scale. Once life starts on a given planet, mostly where the biosphere is varied, it is likely to reflect the planet's history, remaining stable as long as the surroundings are consistent and adjusting to the challenges presented by new environments as they develop. One expects life to last as long as the surroundings allow any kind of existence. Finally, the proximal planets will be burned, while the distant ones will be deprived of the life-sustaining energy their sun provides, as the central stars of solar systems extinguish and then die in a final explosive release of energy. The ultimate fate of life in all places is represented by the quite likely extinction of life on impacted worlds. It is rare to find complex ecosystems populated by significant species with high information processing capacity, termed intensity. Even more uncommon is the progress in technology. Still, it is quite likely that these events have happened and are now in progress in far-off parts of the universe. The coming of technology changes the course of life's development. Technology profoundly affects the surroundings and can create machines with the basic features of their biological ancestors. This creates the possibility of substitution as well as competition. In worlds where intelligent organic and maybe mechanical life forms, space travel presents a workable substitute for extinction.